Now, yesterday we have discussed about the electric current, and we defined what is electric current, SI unit of electric current, and we have also told that there was mainly two types of electric current. One is called DC and other is called AC. If direction of the current does not change with time, then it was called direct current, and if the direction of the current reverses in a regular interval, then that current was called alternating current or AC, which will be discussed later on in detail. Now today we are going to discuss about the electric current in a conductor. Materials are divided mainly in three types, in three different categories. One is called conductor, second one is called insulator, and in between these two materials there is a material which is called semiconductor. Now conductor is those material which can conduct charges. That means in a material in which charge can travel is called conductor. Charge can travel easily is called conductor, and the material in which charge cannot travel is called insulator. Now we are going to discuss the electric current in conductor. How current flows through a conductor, we are going to that part. Now everyone know that bulk material is made up of many molecules, right? And molecules are made up of atoms, and structure of atom we have already studied that in atoms and molecules the negatively charged electrons and the positively charged nuclei bound to each other by a strong electrostatic force, and thus they are not free to leave the material or leave the surface of the material in general. Now we know that atoms have a nuclei which is a very small region, very small region of an atom, and the electrons which are negatively charged revolving around that nucleus. That is nucleus, is made up of protons and neutrons. Protons are positive charged and neutrons are neutral particles. That means most of the masses of the atom is centered at the center, that is called the nuclei, and electrons, which are very light materials but negatively charged particles, are revolving in different orbits around the nucleus. Now in different orbit, electron can reside a fixed number. In the first orbit, a maximum number of electrons that can revolve is 2, and second orbit is 8, etc. Now if we consider the outer orbits, then the distance between the electrons in the outer orbit and the positively charged nuclei increases, and we know the electrostatic Coulomb force is inversely proportional to the square of the distance between the charges. Therefore, if in the outer orbit less number of electrons, then in both the cases charge is less and distance is greater. Due to both these two, forces on the electrons due to the nuclei is very less. Some of these electrons get some energy and it can emit or it can leave the atom, but these electrons cannot leave the material. These electrons, which are loosely bound to the atom or loosely bound to the nucleus, are called the free electrons. In conducting material or in conducting metals, these free electrons, number of free electrons are very large. And in insulator, this number of free electrons are very less. And in semiconductors, the number of free electrons is very less compared to the conductor, but a large amount compared to the insulator. That's why these materials are in between the conducting material and metal conductor and insulator. These are called the semiconductor, which will be discussed later time. Now, these materials, which are called conductor, possesses a very large number of free electrons, and these free electrons can freely move within the material, within the bark material, but cannot leave the material, right? Now, when there is no electric field, that is, in absence of electric field, these electrons, these free electrons can move due to thermal motion, and they collide with the positive ions. From where we get positive ion? The free electron. Which are free electron? The loosely bound electron, which leave the atom, and the free electron who leaves the atom, that atom gets positively charged, and that is called positive ion. But they are fixed in a position. Rather, we can call they are vibrating. That positive ions are vibrating in a particular position. They cannot displace from one point to another point. They are fixed in metal. Now, the free electrons, which are free to move inside the metal or within the metal or within the conductor, they are moving from here and there due to their thermal motion, and during their motion they collide with each other and also collide with the positive ions, and due to this collision, due to these collisions, they come to rest, and again due to the thermal motion they can move. So the direction of the motion is random due to these collisions. Direction of the thermal motion of the free electron is randomly changed or is random due to the collision. It collides with the positive one and changes its direction. Again it collides with the electron, it changes its direction. Thus, we can say the motion, thermal motion of these electrons in absence of an electric field is random. At a particular instant of time, there is no preferred direction. There is no preferred direction. Mind it, remember it. There is no preferred direction of motion of the electrons. Thus, on an average, the number of electrons traveling in any particular direction will be equal to the number of electrons traveling in the opposite direction. So we can say there will be no net flow of electrons, right? That means if we take a bark material, there is a large number of free electrons, and due to thermal motion, let us say a large number of free electrons is moving from left to right, and this number of electrons, let us say 1000 number of free electron is moving at a particular instant from left side to right side. But on an average, you can see that near about 1000 number of free electrons is moving or traveling from right side to left side. That means on an average there is no net flow of electron. That means there is no net current. So, though electric conductor or conducting material or conducting metal possesses free electrons and they are moving here and there, they have random motion, yet they do not constitute an electric current in absence of electric field, because on an average there is no net flow of electrons. That means there is no net flow of charges. That means electric current is 0. Now let us say, or let us discuss what happens when this metal is placed in an electric field. That means, let us say an electric field is applied across this material by providing a cell or providing a potential difference across the material. Now what happens? Since this side is connected to positive terminal of a cell and this side connected to a negative terminal of a cell, that means this side is in higher potential and this side is in lower potential. So there is an electric field inside the material from this side to this side. Now what happens? Now the free electrons experiences a force in a direction opposite to the applied electric field. Since electron possesses negative charge, so the force on an electron will be equal to E into E. If E is the external electric field, now every free electron experiences a force this. Since E is negative, so the force will be in a direction opposite to the applied electric field. That means every electron will experience a force on this direction, and that force is equal to this. You could put here a minus sign, but that only indicates the direction of the force. We have already told that the direction of the force is in the opposite direction to the applied electric field. Now, due to this force, the free electron experiences force. Now what happens? There will be an acceleration, right? There will be an acceleration. So it tries to move in this direction, but it cannot move a long distance. After traveling a very short distance, it will collide with a positive ion, because there is very large number of positive ions also, right? Or you may say there is large number of atoms also. All atoms are not ions, because from all ion electrons does not leave. Therefore, inside the material there is a large number of what? Free electrons, large number of positive ions, and also large number of atoms. Now the free electrons experiences a force in this direction, so they want to travel in this direction, but after traveling a very small distance they will collide with ions or atoms and stops. But the electron cannot stop for a long time, because the electron experiences a force due to this external force. So again he tries to move in this direction. Let us say one electron is here, right? The electron experiences a force in this direction, so it will try to move in this direction. After traveling this small distance, collide with a positive ion, so stops. Then again the electron experiences a force, so again he want to, or the electron want to move in this direction. Again he collides. Like this, the electrons will moving from lower potential region to higher potential region in a very small velocity, or very small velocity. That is called drift velocity, right? As a result, the electron starts moving within a very small velocity, which is called drift velocity. In the direction, in which direction? In a direction opposite to the applied electric field. Now we come to another quantity, which is called drift velocity. What is drift velocity? What is drift velocity? Drift velocity is defined as the average velocity with which free electrons in a conductor get drifted in a direction opposite to the applied electric field. Opposite to the direction of the applied electric field. This is drift velocity. Drift velocity is nothing but a very small velocity with which free electron tries to move within a metal or within a metallic conductor in a direction opposite to the applied electric field. Now we are taking a conductor which is placed in an external electric field E, and which is this external electric field is given by a potential difference between across the material. Potential difference is V. Let us take length of the material. Conducting material is L. Length of the material is L. Like now, since each and every electron experiences a force F is equal to minus E into E. This minus is due to, or is this minus just signifies the direction of the force is in opposite direction to the applied electric field. Therefore, acceleration of each free electron is equal to what? Is equal to F by m. That means minus E by m, where m is the mass of the free electron or mass of an electron. This acceleration lasts for a very short time interval, because after very short time interval, traveling a very small distance, it will become zero, because it will collide with the positive ions or positive vibrating ions of the conductor. So the average time interval between two successive collision between the electron and the positive ion of the conductor is known as mean free time, or you can say this is relaxation time, and it is denoted by tau. Tau is the relaxation time. Clear? Now we are going to find a relation between applied electric field and the drift velocity, right? Let us say every free electron possesses a thermal velocity which exists in absence of electric field also. Now let us consider ith free electron, and the initial velocity, or you can say the velocity just after a collision. We are considering a particular collision, or we are considering a particular time interval. Let us consider the velocity after the last collision is Vi. Vi is the velocity of the free electron after the last collision. That is, it is the initial velocity which we are going to discuss. Right? Now this is due to the thermal random motion, right? Because just after collision, the velocity is zero, but there will be a thermal motion, and due to that thermal motion, the velocity is Vi. Now let us say that after time interval Ti, it will collide with another positive ion. So after time interval Ti, the velocity of that free electron will be equal to Vi plus A, that is acceleration, into Ti, because after time interval Ti it will collide. Now we are just taking the magnitudes. That means we will write acceleration is this. Therefore V equals to Vi plus EE by M into Ti. This is for ith free electron, right? Now there is a very large number of free electron inside the material. So you have to calculate these velocities for every electron and then take the average. And that average velocity is the drift velocity. Is it? Now the V average, that is the drift velocity, will be equal to Vi average plus EE by M into Ti average. Now we can say this as 0. Vi average is 0. Vi, what is Vi? Vi is the velocity due to thermal agitation or due to thermal motion, and these velocities are random, that is in different directions. So when we take the average of this velocity, that will be 0. So we put this as 0 and EE by M and Ti average is tau. We already discussed that Ti average, that is the average time between two successive collisions, is relaxation time, and that is written as tau. So we can say Vd equals to EE tau by M, which is the drift velocity of the electron. You have to put here one minus sign because of E, which is negative for an electron. So the direction of Vd, that is direction of drift velocity, is in the opposite direction of the applied electric field. Again, you see here Vd is proportional to 1 by M, that is drift velocity is inversely proportional to the mass of the charge carrier. Now here mass of the charge carrier is electronic mass. If there is another charge carrier then of different mass, then the drift velocity of that charge carrier will be different from this electron. Now we are defining another quantity which is called mobility. Mobility is the drift velocity per unit electric field. Drift velocity per unit electric field, that is drift velocity of a charge carrier when it is placed in an electric field of unit intensity is called the mobility of that carrier, charge carrier, right? Or you can say mobility is the ratio of drift velocity to the electric field, applied to the material. Is it clear? Now mu is equal to Vd by E, that means E tau by M. E tau by M is the mobility. Thus mobility of a charge carrier or current carrier is inversely proportional to the mass of the current carrier. Now in metallic conductor there is only one charge carrier, which is electron. We will discuss in later time the semiconductor. In semiconductor there will be there are two types of charge carrier. One is electron and another is called positive hole. Now, the positive hole has the mass greater than the electrons. So, you can say the mobility of electron is greater than the mobility of hole. That will be discussed later on. Now, you have to just remember about the mobility. What is mobility? Mobility is the drift velocity of current carrier when the material is placed in an unit electric field, or you can say the drift velocity per unit electric field is called the mobility of the current carrier. Now we are going to establish a relation between current, electric current and drift velocity in a metallic conductor. Relation between drift velocity and electric current. Let us consider a cylindrical metallic conductor of cross-sectional area A, length L, is placed in an external electric field. We provide a potential difference across the material is V. Therefore, applied electric field is in a direction from higher potential to lower potential, and that electric field, that is intensity of the electric field, is V by L. We know from electrostatics E is equal to dV/dx. Therefore, E equal to V by L here, applied electric field. Now let us take two parallel cross-sectional area separated by a distance Vd. Separated by a distance Vd. Now think about this cross-sectional area. This cross-sectional area, right? What is electric current? Electric current is the amount of charge flowing through any cross-sectional area in unit time, right? Now let us say small n is the number of free electron per unit volume of the conductor. This is number of free electron per unit volume. M is mass of the electron, E is electronic charge of the electron, etc. Now, can we say that the total number of electrons inside this region will cross this cross-sectional area in 1 second? Can we say that? Since drift velocity is Vd and length of this cylinder is Vd, therefore the free electron which is at this position will cross this cross-sectional area in 1 second, because drift velocity is Vd and the distance of this point to this point is less than Vd, therefore this will cross this cross-sectional area. Similarly, the free electron which is at this point will also cross this, because the electron will travel Vd distance in 1 second. That means if this is Vd, then this electron will come to this point in 1 second. So the electrons or free electrons which are inside this region will cross or will travel through this cross section area after 1 second. So now, what will be the number of free electrons inside this volume? Now see here, this is a cylindrical volume also, whose cross sectional area is A but length is Vd. So volume of this region or this cylinder is A into Vd. This is the volume. Now the total number of free electrons inside this volume is N into A into Vd, because N is the number of free electron per unit volume, and the total charge inside this volume is NaVd into E, is the electronic charge. And we have already told that the free electrons inside this volume will cross this cross sectional area in 1 second. Therefore, the charge flowing through this cross section area is equal to this in unit time, that is in 1 second. Therefore, the charge flowing through this cross section area in 1 second is this, and that is the current. Therefore, current in this conductor is Q by T, that means Q by 1, because T is 1 here, and that means NaVdE by 1, that means you can say I equals to NeaVd. This is the relation between drift velocity and current, or current is related to drift velocity. And on this also, Vd equals to I by Nea. This is an expression for Vd, that is drift velocity. Or from here you can also write I by A equals to NeVd. Now this I by A is the current per unit area, which is called current density J. Current density J equals to NeVd, and this current density is a vector quantity and it is in a direction of the drift velocity. That means you can say J equals to NeVd. J vector equals to NeVd. This J, which is called current density, that is current through unit cross section area.